Always setting this talk, I just want to make a very informal and personal statement that in 1992, which is over 30 years ago, Moffat, which now is coming here, invited me into this research wasn't Trinity College, and Kit was actually sitting in Newton's old office under Portland Lodge. So it's one of the most unforgettable experiences in my life, and so I personally want to thank Kit for this. And now, before I go into my talk, which is a very specific piece of turbulence theory, I just want to make a few remarks maybe for younger people, because some things we explain to our students behind closed doors, and they're usually motivations. Why the hell we're doing this, and why the hell we're doing this? And I'm trying not to look at all the team which you organize, this anti-diffusion pattern formation. It's something about appearance of order in a statistically disordered system. And then you ask, there are kind of so many orders appearing, because of, there's kind of randomness in a sense. Let's say a Gaussian set of non-correlated harmonics, and then you see order appears. So you ask what terms you need to describe it. Most general terms. And the most general term to describe order, at least from a most general perspective, is entropy or information. Right? You can ask how much you lowered entropy with respect to this most disordered state. This would be a most general way to describe it. That what we are not doing here. Right? We are mostly working either on the very engineering side of things, saying, okay, we'll make it rotating, or we'll make it stratifying, or we increase amplitude. It's all kind of engineering approach. Or we move a little bit further and we say, yeah, it's, we're kind of making a inverse cascade, etc., or we're doing fluxes. But what we need to be asking is the following question. So order appears, it lowers entropy, which means that we somehow have a system which has a constraint on it. Right? Without constraint, it would go to maximal entropy and live there. The way we lower entropy, we impose constraint. What kind of constraint we are discussing here? Well, inverse cascade means we have extra invariant, we have energy invariant, we have entropy invariant, we have extra invariant in imposes constraint. Inverse cascade creates order, it's self-organization. This constraint could be topological. This constraint be something in dynamical terms, right? Again, the moment we start talking in these terms, and we will at some point, that's why I'm mostly addressing younger people, that would be entropic way, namely we say, look, this is the entropy maximum under given constraint. It's very difficult. For 40 years, I'm trying to ask myself in the most simple cases that I know, simplest non-equilibrium states, it is entropy maximum under what condition? And I cannot answer it, not only for turbulent system, but for much bigger system, right? So what now I want to show in a very particular, and it's very recent, it's still unpublished, just submitted to PRL, paper, one way to look into turbulence. The simplest case of turbulence I know is a set of turbulence of weakly interacting waves. So we're looking at a sea at a very, very mild excitation. What we see mostly waves running around of a very low amplitude. Nonlinearity parameter is just an angle. It's 10 to minus 3 over, well, 5 10 to minus 3 over here. And then we ask how to describe it. Well, the most natural description, as I will write, this will be all analytical work, no numerics. It's just as a set of weakly interacting waves, and the statistic will be close to Gaussian set of weakly correlated Fourier harmonics, which naturally corresponds to a maximum entropy under a given energy. And then we increase amplitude. That's what we see as the same system. We start seeing, of course, there are a lot of small waves running back and forth, but we start seeing some kind of patterns. We can do it to other systems. We can take a fiber and run many, many harmonics, and it will be weakly interacting. Increase amplitude, we'll see solitons there. It's a different type of self-organization. or we can increase amplitude and we don't see this type of pattern formation. Okay? So what I'll try to do, using standard tools of quantum field theory, essentially statistical physics, I'll try to describe set of weakly interacting waves like this and ask what actually tells me by looking at this system that at larger amplitude it would have this type of order of these patterns appear after it. Okay? So the language will be more or less perturbation theory. This is a work done with Vladimir Rosenhaus. This was already in the archive last year. And it took like 2 years to write like 25 versions, but it essentially, a few weeks ago, it was submitted. So I define turbulence not as a fluid flow, just as a state of a system very far from thermal equilibrium. So there are many harmonics far from equilibrium, and I'll consider, to describe this set of waves, a very particular class, which will be just described by this Hamiltonian. The first part, quadratic part of a Hamiltonian, describes the linear part of the equation, namely every Fourier harmonic just oscillates with its own frequency, and I assume that there is a 4-wave scattering, 2 waves scattering to other 2, and this is okay for gravity, for long waves on the water. This is a first resonant interaction, so this is my equation of motion. And of course, I assume that lambda is very, very, or amplitude, so this term is much, much smaller than this. Theoretician's dream, I have a small parameter, I have a simple Hamiltonian equation, I just need to run perturbation theory, which we all were supposed to do when I was doing my PhD 40 something years ago, or when my teacher, Zakharov, did his PhD at 60s. Nobody did it until, Polyakov was supposed to started to do it at 90s. Just do straightforward perturbation statistical theory with this equation. Believe it or not, it's only being done now more or less consistently. But what we expect, right? You don't do complicated computations before you sit and ask yourself, what do you expect out of it? And one of the things that we learn from great people at 60s, 70s, and 80s is that, first of all, you expect from this perturbation theory to see renormalization of the parameter of your Hamiltonian. Namely, if you run a single wave on a C where there are no other wave present with a given k, its frequency will be omega k. If you run a wave and there are many other waves present, this frequency will be different. We call it frequency renormalization. The same thing when you scatter 4 waves on quiet C, you would be described by lambda. The energy of such scattering will be lambda. If you do it in turbulence, it will be something else. And what we learn from great people at quantum field theory is that there is a very interesting way and very particular class system. It's very, very rare when you can compute this renormalization. So this is lambda, it must be lambda tilde, it's a renormalized lambda. It's your bare lambda from which you started, a given wave number, and all the terms which are related to kind of higher terms sometimes could be summed into a geometric series which give you something like this. This is more or less what people did in quantum electrodynamics and in quantum chromodynamics for 2 different cases, and the main distinctions that they've seen, and with which I will return, is the sign of this beta. Essentially, it's a very simple question. Whether other waves enhance or suppress interaction of a given quartet. That's a very simple question, right? Essentially, in electrodynamics, you ask the following thing. So you have one electron and you have another electrons, right? Well, but it's a quantum system. You do quantum electrodynamics. It means that vacuum fluctuates in between those electrons. There are pairs on these pairs in between. You ask what they do to these 2 electrons. We know the answer. But every time that electron-positron pairs appears, electron will be a little bit closer to this guy, and this positron will be closer to this guy. They will do screening. All this fluctuation will do screening, which will turn into the fact that your beta will be positive. So you suppress the things, right? That's what quantum fluctuations, or in this critical phenomena, that's what they do to your bare interactions, right? So if there would be no quantum fluctuation, you would have Coulomb's law, but then now Coulomb's law is getting renormalized. The further and further are two charges, the weaker and weaker they interact faster than Coulomb's law would predict. On quantum chromodynamics, it's totally opposite, and that's what makes life so interesting, is that this beta is negative. So this beta is negative means that surprisingly, you take one quark, you take another quark, you move them further away, they interact stronger. You move it even further away, they interact even stronger. As if there is some elastic ribbon in between them, and we of course now have all this hypothesis and fantasies, what is actually made of, and all this monopole stuff. But in terms of just pure computation, your beta is negative. And you compute it in a very simple way. That's Frank Wilczek, PhD. I mean, most of the things here are done by PhD students that I'm talking. Okay, so it tells you the following thing, the most dramatic thing out of it. At some point, it can turn to 0, right? So you increase this log, you go further and further away, your beta is negative. No matter from how small lambda you started there, at some point you reach the 0 in the denominator. What happens? It sends you a signal. And now we know, I mean, 50 years after Gross-Wilczek work and many other people, what happens is a kind of a phase transition, but not phase transition in terms of equilibrium statistical physics. You cannot use the language that you're using. And the language we're using here is the language of AK. It's the language of plane waves, or electrons, or quarks and gluons in quantum chromodynamics, which works nice when this denominator is far from 0. It stops working when you approach 0, and it sends you a very simple message that something else now is a building block of your system. And it's usually bound state, which we call hadrons, which is built out of quarks and gluons, which you cannot separate because you're now at such a large distance that you don't see separate quarks. Okay? That's more or less inspiration for the words that I'm going to tell you. This is something which was done when I was a student, and then we were learning it, and I was starting doing this computation, I don't know, I don't say how many years ago, and then I gave up because I didn't understand what to do. But essentially, this mental picture with which now we do and work on, and again, it's a question what kind of pattern you expect. Whether you expect that your kind of screening would make your interaction effectively weaker and weaker, which is by itself a nonlinear effect, or you expect that some new object which would be very, very coherent bound states of your initial plane waves. Okay, so now let's do it. It's just relatively straightforward computations. So we write this equation, we multiply this equation of motion by AK complex conjugated, we add complex conjugated equation, we get equation for the second moment, which sometimes is called occupation number of waves. It's proportional to the imaginary part of the force moment, usual closure problem. You say that at this point, when you assume that your statistics is close to Gaussian, namely described by this way, this is just 0. This cumulant, and for Gaussian field, the cumulant is 0, it's an imaginary part, real part is not 0. Okay, then you start iterating it, namely, technically, there are many ways to do perturbation theory. One simple way is you add to this equation random forcing, and then a dissipation. You assume that this your random forcing and your dissipation in some kind of limit, when at the end you would turn this amplitude, which is this one, and that gamma into 0, but you'll keep this ratio. It's kind of standard. There are different ways. You can average over initial condition, you can average over random forcing. You expect the system that it somehow non-linearly will bring you where you want to be. And now you just iterate. Yeah, that's pretty simple. So you have this expression. So you do Fourier transform. This is your equation. This is your Fourier image of your forcing. This is your nonlinear term. Sorry, your omega is, I mean, all the linear terms to the left, forcing your nonlinear term. Now you iterate. So the first iteration give you just this, and then you substitute this f's here. So you get cubic terms in f. Then you got quintic terms in this. What I want to stress here, for particularly for young people, it's a straightforward analytic calculation. There is no, I mean, Poincaré did. Right? This is something which is doable. There's no. Sometimes you open a textbook in quantum field theory and it looks scary, and you think, okay, well, that's probably so. No, it's a very straightforward computation, analytic computation. You can get a lot of new physical results still doing this stuff, right? It is not dead. Computers did not replace it, believe it or not. There is no computer that can model a system of, I don't know, 20,000 waves, but analytically it's pretty easy. Anyway, so on the first step, when you just write this first non-vanishing expression for your force 4 point, which was here at the right, it's just proportional to n. Right? So this is something which is ddt of a fourth order equal to 6th order. 6th order you replace by n, usual Gaussian or weak decoupling, and that's kinetic equation. It was derived by another PhD student, Rudy Parles, in his PhD in 1929. Everything was done here. And it was solved by another PhD student, Vladimir Zakharov, who found a very non-trivial solution of this equation. It reminds kinetic equation. One of the most applied equation in the model engineering in science are kinetic equation. Boltzmann equation is this equation. It's a closed equation. It describes a lot of amplitudes, complex numbers, with phases, by a single scalar quantity, which is a function of k, and it's closed. This is Boltzmann equation. It's very simple. These two equations are two limits of one quantum equation. You go quantum numbers much less than unity, you get Boltzmann, you get much larger than unity, you get Parles kinetic equation. Good. Now, what I'm going to do, first did people for Boltzmann equations. That's why I actually gave you this example. They ask what actually happens if you try to account for corrections to Boltzmann equation. Boltzmann equation, you see, it describes pair collisions, like us. So what happens if we describe that these two particles collide, then this particle collides with other particle, return and collide again with the same particle as before? So great people at late 60s and early 70s ask this question, and then they say, well, look, you need to integrate over all position of a particle 2 after which you return to a given particle. If you want to account for, not for triple, but for fourth collision, you need to integrate over position of 2 or position of 4. So your corrections to Boltzmann equation appears out of account not for 2 particle scattering, but for 3 particle, 4 particle, 5 particle, etc. And they immediately hit the difficulty which I hit when I did my PhD. This correction diverge. Because when you try to integrate over position of a particle 2, yeah, you see at order n, it's proportional to the distance to this particle r, and of course, to return, you need to get back into the scattering angle, which is inversely proportional to the distance. It gives you this factor minus d plus 1. This is your solid angle in which you need to be to return back. It diminishes the probability. But a phase volume gives you r to the power n. Starting from n, you diverge. Which means that those corrections are infinite. Well, they're small, they're proportional to your density in some power, and density is a small parameter for Boltzmann equation, but they all diverge. It's infrared divergence. It was noticed probably 69, 70. And what is really, you ask, well, is it real? Well, it's real, because in one dimension that it starts diverging immediately, which means that in one dimension there is no fluid mechanics. There is actual kinetics, is very non-trivial. You have multiple collisions of the same particle. It's a very active area of research now. In 2D, this divergence starts from n equal to 2, and they are logarithmic, and it's very non-trivial correlation function in a response function in 2D. So it's very, very real. But then what they understood is that, of course, the answer is finite, right? For example, you want to compute equation of state, how pressure is related to density. First order linear term in density, which is ideal gas, would give you Boltzmann equation. It's correct. What is the rho squared correction? Is it divergence? You put all this, and then you miraculously found that all these divergences cancel out in any equilibrium state, and then you understand that there's probably Dorfman and Cohen were first to understand that it's really because of detailed balance. Okay. Then you try to do non-equilibrium, which we'll be doing here. And they started to compute transport coefficient. How you do it? You impose a gradient of temperature and you compute flux. Or you impose a gradient of velocity, you compute viscosity. And they found that for kinetic coefficient, those cancellations are absent. Because you broke detailed balance, that now all these divergences are real, you need to handle them. But we all know that diffusivity or viscosity of any gas is finite. So what the hell going on? You write Boltzmann equation, gives you a finite answer. You compute correction, gives you infinity. Any idea? The idea was that what you are doing is, again, you're doing naive perturbation expansion. You assume that every time this particle runs to this particle 2 could be like at arbitrary distance. Well, excuse me, there is particle 5, particle 6 could happen on your way. And this collective effect, which in principle include interaction with as many particles you can imagine, impose a finite mean free path, which actually is a cutoff, infrared cutoff for your integration. And that was exactly at the same time where people in chromodynamics did their computation. So they actually did this collective effects. They got this correction. They found out interesting things, namely the summation of all the things led to the logarithm, exactly like this logarithm over here, which means non-analyticity. But it was all finite. So your perturbation theory is non-analytic because you need to do partial resummation of infinite number of terms. And that's also what we'll be doing. Okay? So now let's get back to our system and let's do what we're supposed to do, but now we'll be working with a non-equilibrium of a different type. Their non-equilibrium was transport. Namely, they impose fluxes in space. We'll be doing turbulence. Namely, we impose fluxes in Fourier space. And that was another PhD student did, as I already mentioned. Zakharov did it. He took this kinetic equation written by Peierls and found a solution which corresponds to turbulence. You can guess the form of the solution pretty easily. This equation conserves number of waves and it conserves energy, which means that it could be written, for example, for energy in the following form: that the time derivative of n omega k is just a spectral density of your energy must be its continuity equation, right? Because it's conserved quantity, so it must be divergence of some flux. Now you can require your flux is equal to constant. That's your turbulence solution. And just by power counting, you find out this solution, which is Zakharov solution. It expressed only in terms of space dimensionality and scaling exponent of this lambda. So you assume that this lambda has a degree of homogeneity beta, and that's how you get this solution. It's like power counting, but now you need to prove that this is a solution. You need to plug it into this equation and show that all terms cancel each other. Because now it's not equilibrium, it's a non-equilibrium solution. It has a very non-trivial. In my PhD, I've shown that it cancels because it's somehow the scaling exponent corresponds to what we call counterbalance locality. So it interacts with short waves and with long waves the same. That's what balance is. But Zakharov, for the first case that he did in his PhD, just substituted it for simpler ways. He computed 18 integrals and they all cancel. Heroic act. And but for this, it's also important that all the contribution of interaction with very long waves and very short waves all converges. We call it locality. There should not be non-locality in the sense that interaction should not increase when the ratio of K1 to the K2, let's say, to two interaction waves increases, right? Like we had this thing for particles. Okay, so now we'll do the following thing. We have an equation, we have a solution. What are validity conditions for this equation and for this solution? And we need to say, I mean, look, this whole perturbation theory, which means that we assume that the second term of a Hamiltonian is much smaller than the first one. So let's just take this lambda multiplied by, so the ratio between this and this is essentially this ratio. Because this is a to the 4, this is a squared, you could say that this is nk, there is extra integration. we call this parameter, and it's written in our book with Zakharov, and it's like in every text, in Nazarenko book, in every textbook on wave turbulence, it said, kinetic equation is valid and Zakharov's is his solution if this parameter is small and all integral converges. This is wrong. And so now I'm destroying what I did many years, but it's getting much more interesting. So this is essentially a simple dimensional estimate. And the statement is, if all integral converge, then you can estimate any integral just by power in front, just by counting its degree of homogeneity. So as you probably already guess, the moment you go to higher orders, like for, this is books on wave turbulence, this were actually all the wrong statements that I mentioned, they were made in this book. With Zakharov, we're now doing second edition, so at least there will be fewer wrong statements. Now to analyzing, and I won't go into the details of analyzing integrals, they depend on different asymptotics of lambda. If there is one general lesson, which I don't want to go into computation, the general lesson is as following. If you look at equilibrium, it's actually determined by only omega k. So if you ask what is the equipartition, it's omega k time n k equal to constant. It's called Rayleigh-Jeans distribution. It does not care what lambda is. So it doesn't matter what is the interaction of waves. You need interaction to establish equilibrium, but the form of equilibrium is independent on lambda. Zakharov's solution, which was just written over here, depends only on scaling exponent of lambda, of this beta. It does not care of the form of lambda. How actually it depends on angles, etc. Everything from now on, which I start talking, namely contribution of higher orders, will depend on very, very specific things in lambda, and this is a general lesson. The farther you are from equilibrium, or the higher you are on linearity, less universality you have. That's the price we pay. There is no free lunches, unfortunately. In a sense, all this work that it is just the beginning of, there are now many people doing many things here, is how non-locality enhances non-linearity far away from equilibrium. So all three troubles they all will have here. Far from equilibrium, first it will be weak non-linearity, then it will be stronger because of non-locality. Let's see how it works. So we analyze locality, and then we do next corrections. And I probably briefly skip corrections for omega. This is an interesting subject, and if somebody is interested in Gross-Pitaevsky, nonlinear Schrödinger, plasma, turbulence, there are many interesting things which appear already from renormalization of omega. But I want to talk about things which are similar to quantum electrodynamics, quantum chromodynamics, so I'll be mostly talking about lambda. What happens to renormalization of the interaction if we account for many interactions? This is just the first correction. This is the first correction, which is schematically you can imagine that there are waves 3 and 4 not going directly into 1 and 2, but first going into 5 and 6, and then this 5 and 6 produce 1 and 2. So essentially it's just kind of 6-wave interaction, but very similar, like one particle hits this particle, hits this, and then return hitting back to this. This is our analog to the first corrections that Dorfman, Cohen, Oppenheim, and other people did. And those are integrals. It's just straightforward. Took about 3 days to compute. Not that, terrible thing. Just do it. Well, overeducated field theorists compute it in 15 minutes. They have tricks. I do it in 3 days, which is still the same answer, which is pretty reassuring. And then you start analyzing integrals, and you find out that this damped correction, when you plug there, equilibrium just vanishes, like for Boltzmann. When you plug there the Zakharov solution, they diverge, just like Boltzmann. Unfortunately, they diverge on both ends. They diverge on UV, namely at very large K, and they diverge at infrared. And these divergences are of kind of a different nature. And then you start looking into it and analyzing. So I'll probably, this is kind of a personal remark. I did this computation 40 years ago when I was a PhD student. And I've shown it to my teacher. And I was like, well, you look at the C. This is maybe 1 decade of scaling, maybe 1 decade and a half. So what is your correction, it's small because your waves are small, and this kind of, nothing interesting. Well, it probably means something. And I gave it up, and only later I've learned from field theorists a very important lesson, which I also want to say like lesson, again for younger people. Anytime you do correction, you see divergence, it's a very important message there. So for any field theorist, any divergence in the perturbation theory, it's a message. It tells you that something is wrong with your basic assumption, or it tells you that you need to account for something else. That's what all the normalization group approach to critical phenomena is actually based for, and it took me some time to really understand that this is a gift and not a nuisance. This is an instrument. And in particularly, there is a very, if somebody were to learn it on the most elementary basics, there is, of late Joe Polchinski, a very great, just archive articles, which probably called like this, like divergence is an instrument. And that's where I learned this way that very often just by doing simple first order correction, plug in the solution and seeing divergence, you can understand a lot. So let's see what we can understand here. Again, all these divergences depend on all this asymptotic. There is a lot of different things. And then you look at it, and you, in particularly, there are kind of different contributions. You need to analyze them. And in particularly, when you look at this UV contribution, namely the divergence which comes out of, you will see cancellations between different terms. And interestingly, they come to this combination, which particularly in this town, people, well, in UK in general, there is something which is lambda, which is the sign of your nonlinearity, is your coefficient of first order interaction times second derivative of omega with respect to wave number. And they, in classical or in condensed matter, call it Bogolyubov spectrum of condensate perturbation, and we in fluid mechanics call it Lighthill criterion for modulation of instability, or Benjamin-Fair instability. So if we would study a monochromatic wave with a given k, and we ask if it's stable with respect to modulation, we would discover that, I guess I probably wrote some formula for it. No, I didn't. Anyway, it's a textbook stuff. So the wave is unstable if its lambda times omega 2 prime is negative. Namely, the correction to frequency because of nonlinearity has the opposite sign than because of dispersion. What I found, to my great delight, that the question whether this is your enhanced or suppressed, this is your correction divided by your lambda. It's something which is even, lambda could be any sign, incidentally, and this a person at the back, Natalia now computes it for gravity waves. It's a very complicated function of wave number. What stands here is a ratio. So you actually ask about its sign. And its sign depends on Lighthill criteria if you account for this interaction with a very short wave. Again, it's a very particular result. It's a first order correction. And this first order correction already somehow gives you some kind of a turbulent analog of Lighthill criterion. It tells you, you want it negative, it will be like, then it will go into the denominator, it will be like quantum chromodynamics. Anyway, then you go further, and then you start analyzing next term. And then you're out of your depth immediately, because you have only two types correction and just 6 terms for next order. But when you go to higher order, to two-loop diagrams, there are 70 terms immediately, and it's really big. So you need some way to sort it. And what we did, we say, if we have this UV divergence, let's take at the next order only terms with the highest divergences. And they fortunately were the terms that give you squares of your terms in the first order. It took me 5 months, and I don't know what will be in the third order. And my co-author insisted that we say, we make an assumption, and we wrote it by big capital letters. We make an assumption that in all orders, the highest UV divergences would be of the type of a geometric series. I've seen it only on the second order. So making this assumption, we can do the same things that people did for kinetics and that people did for quantum electrodynamics and thermodynamics. We can sum all these terms. Each one has this UV divergence. When they come in the denominator, the resulting integral does not have divergences. So when you do all this, diagrammatically they all look like this, which is a very direct analog of what people did in many other things. And eventually you obtain your kinetic equation, which we call renormalized kinetic equation. Without this term, it would be the old kinetic equation. Now all these geometric series summed into such term. This is L is just a very simple integral. It's a complex number. So you have here essentially plus complex conjugated. And but now if you look at the whole expression and see, and you plug there, you plug here, and you plug here the Harov solution, everything diverged at UV. So we're making physical statement that if our cascade is, and we took direct cascade name, cascade to large K, goes to large K, and our dissipation scale goes to infinity, everything stays finite. No UV divergences. Very much like in the turbulence of incompressible fluid. What remains though is that this integral by itself diverges in the infrared at the low K. And this we don't know how to remove or whatever. After all this thing, this divergence remained. First of all, and it tells us that because this infrared, it contains K naught, which is L, the size of your box or your pumping scale, in the negative power. Because it contains this in the negative power, now when you estimate your correction to lambda or to n, it will be, and this is dimensionless factor, this L. You see, it's 1 minus L. This is what in field theory is called effective coupling constant. So when you compute your correction, if it converges, then more or less it scales like a naive scaling. If it diverges, it means that it's somehow proportional to your smallest wave number in some negative power, and dependence on your K also changes. So this is a new effective coupling, and it's an old coupling multiplied by this K over K naught over power beta over 6, and beta, I remind, is the scaling. This again reminds us incompressible Kolmogorov turbulence in a very unexpected way. Let me remind you maybe the most surprising fact about Kolmogorov turbulence. That if you look at the moments of velocity, then it's something which is P is what is called epsilon in the other talks, is just an energy dissipation rate. So dimensionally it's like this. But what we find out, and we can even prove it for some models like passive scalar, that there will be ratio, this is our 1 over K naught, this is L, box size, in some power delta. And delta changes sign when n goes through 3. For certain moments, this is just a flux. There is no this delta. But for moments smaller than 3, delta is negative. This is something which is really worth appreciating. When delta is negative and L goes to infinity, your second moment, which is the spectral density of turbulence, goes to 0. Let me again say it. I think it's really important. It's very simple. So you have an energy dissipation rate, P. It's flux. It's fixed. Now you increase the number of steps in your cascade. And you ask what would be your spectral energy of turbulence after L over R steps. The answer, it goes to 0. Your fourth moment goes to infinity. What it tells us? It tells us what Kip taught me many, many years ago, intermittence. It tells you that to keep the same flux, to burn the same amount of energy, for very, very long cascade, you need less and less turbulence. It happens in a very, very rare fluctuations, and this fluctuation burns the same amount of turbulence, of energy. So in a sense, how much time I have, Anna?
8 minutes.
8 minutes? Excellent. So it tells us that by discovering this infrared divergency for waves, we more or less found an analog of it, a dependence this infrared means that we depend on the large scale. We know how many steps of a cascade behind us. Not how we did it only for force cumulant, right? So what we computed is a force cumulant. So we don't know what happens for higher moments, nothing like this. But this is something which makes it a little bridge. And then again, the most important question, which now will be the last turn, what is the sign of this L? Are we in electrodynamics case where 6-wave, 8-wave, 10, 12-wave interaction suppresses 4-wave effective scattering? Or that means in our case L is negative, right? So that it's something larger than unity in the denominator and it suppresses. Or it enhances it. Okay? And what we did with Vladimir, we essentially computed it into very unphysical, the simplest system where this lambda is just K1, K2, K3, K4, a product in the power of beta. There are some systems like nonlinear Schrödinger where this beta equal to 0, where there is no such interesting divergences. But essentially, it's a question which we now need to analyze for every physical system. And in particularly, we are now doing it with Vladimir, and this is something which is about waves for which I started, waves on the water. And it happens that, first of all, lambda, where lambda itself changes sign depending on configuration. If there are waves scattering like this, it's usually positive. With this, it's negative. And then correction could depend on it. And when the wave scattering like this, it could have a different sign. At this point, we don't know the answer, unfortunately. I can tell my speculation, and then in 2 years from now, you can confront me with my speculation and say, aha, you told this is wrong. But what I think, that by seeing this Stokes-like cusps over there, tells me that strong interaction is for locally parallel waves because it creates almost one-dimensional front. So what we are looking at, what I very much hope, and this will be already numerical work, because it's a very complicated now integrals. It's a given integrals, but in 6-dimensional space, I think that there will be enhancement of interaction for waves, which are more or less has almost collinear wave vectors. And this enhanced interaction would create bound states. Those are our hadrons. This is a bound state of many plane waves. And I'm not saying something non-trivial. Any fluid mechanicist knows that the shock wave is a coherent state of many plane waves, right? So you need many plane waves with a very peculiar phases to create a shock, or to create a cusp, or to create a Stokes wave, which is asymptotically a cusp. But the hope is that by looking at our normalization, we can find out that collinear combinations more or less enhance and perpendicular are not. And for some other system, it could be that the perpendicular combination enhanced, and there will be system which work with creating soliton-like state. Or there could be system for which will be like electrodynamics, that any high mode interaction would just suppress your basic interaction, and strong turbulence would look completely different. So as I'm now approaching the end of time, again that I mentioned this Light-Field type criterion, and I really skip all the beautiful thing which we, maybe just I say one word, that if you try a little bit more different lambda, a little bit more complicated, it changes. It's a very, very, so we're very far from classifying universality classes here. We just know that it's now much less universal. So this is my take-home lesson. This is the question. We see that non-locality, which related to UV, seem to be irrelevant. Again, like for infrared divergence for Boltzmann equation, it makes your perturbation theory non-analytic, but it doesn't make corrections large. They're still small. So when your dissipation number goes to, your viscosity goes to 0, everything stays fine, at least if you don't study gradients. Now, what we find out that infrared divergences are there, and they probably mean what it means for incompressible turbulence. The system always remembers how many steps of cascade it made up to this point. And this dependence is essentially a part of the important information which tells you what you need to control to lower entropy such that it corresponds to this appearance of orders. So this is I'm very far from it, but this really my goal is that at some point I will be able to say, look, the weak turbulence of waves turned into the strong turbulence of highly organized patterns which have much lower entropy under the given energy. If you normalize entropy by energy, it would be much lower, and this is related to appearance of this pattern. And to organize these waves, you need the interaction of all waves from this short to your pumping scale, and that's how you remember how many steps of a cascade you already left behind. But this is more of a dream than of an idea. And so, again, this may be a general lesson, and I'll stop here. Let me finish.
Questions?
Yes.
So I can't resist sort of an obvious question. I mean, this story of non-locality enhancing non-linearity is, of course, the story of what we've been hearing today, particularly in these beta plane models. So I suppose you're pointing toward the hadron as being some bound state of the jet and waves. But I mean, could you elaborate on that for us?
Yeah, in a sense, that most things that we've heard today, they had kind of an evident thing which was inverse cascade, creating some kind of a zonal flow or big vortex, etc. Here, there is no spontaneous symmetry breaking. This is still isotropic systems, right? So in a sense, what I think my hadrons, this is just a bound state of many strongly interacting waves. So a system of weakly interacting waves, as you increase amplitude, start breaking into clusters of strongly interacting waves, and everything else running on the background. So we're starting to describe this type of self-organization, which is not related to any symmetry breaking which you need for jet formation or anything else.
But locally, one of these bound states can break symmetry.
Absolutely. Locally, they break symmetry locally. That's what I try when I ask about that. There, at some intermediate times, you can think that you kind of have a state. When you look at longer time or at larger scale, you realize that actually symmetry is restored because it can switch into other state. So here locally, you have a symmetry breaking. You know, you have fronts. You see similar things in acoustic turbulence for sure. Again, I want to describe it by this language of renormalization. This is an attempt to describe phenomena which fluid mechanicists know pretty well in plasma physics on a language of quantum field theory, right? As renormalization. That's the idea. Then I know cumulant, then I can compute entropy.
Okay, so I think we're out of time.
Oh, sorry.
No, it's exactly time. So thank you very much, and let's thank all the speakers.